Process, you already know once we get oblique shocks or shocks in general, I have a pressure, stagnation pressure loss across there. And I can designate this with some ratio, so stagnation pressure ratio RD is equal to PO2 over POA. If it's isentropic, the stagnation pressure is constant. But since I have shocks, I have stagnation pressure loss. Now, how do I know RD? I could actually use the local information about oblique shocks and normal shocks and knowing the hardware and try to predict it, but it's still gonna be ideal situation because the equations that you used in high-speed aero are still the ideal isentropic equations. So what we use is a equation that looks like this. It's an empirical based correlation. Mach number minus 1 out of 1.35. So this is based on complex shock structure. And this is, since most of supersonic aircraft are military based, this is actually a military standard correlation. So, what this represents is the inlet situations for you don't get a really oblique shock like this in a normal shock, but it's clean in that form. You get a very complicated behavior, and obviously the engine is round, so it's not, you get, sometimes that shock actually separates and you get a bow shock and whatnot. So it really is a function of your Mach number, and this is just a curve fit based on various experimental research data that they've taken and measured stagnation pressure upstream, measured stagnation pressure downstream at different Mach numbers, and based on this data, took the pressure ratios and got this curve. So that's one of the equations for your. This is actually not giving out any trade secrets in chapter 6. So based on this, I could actually get also my temperature ratio. So total temperature ratio. Tau D is equal to T stagnation 2 over T stagnation A. And in this case, when we just did, OA is equal to O2 on the same line within the temperature curve. So we set this to 1. Move it up. So it's assuming that this temperature is actually equal where it's going to be equal to 1. So it depends on the friction coefficient you have. You might actually have some heating, but assuming adiabatic at this condition. Now, from the standpoint of efficiency, we'll assume adiabatic based on this condition, adiabatic efficiency. Of diffuser. So eta D is equal to H stagnation 2S minus H or if you remember, right here, very, look at how much, I don't remember what, which one. Right here. We talked about it in the past where you have non-ideal configurations where you have a real situation and these are the situations you have to deal with in terms of overall efficiency. And that's where it comes right here. So everything that we've been doing in the first half of the semester is not a waste of time. It actually builds up to all this. So this is almost equivalent of our temperatures. So it's the stagnation temperature, the isentropic stagnation temperature at 2 minus the actual temperature divided by the stagnation temperature at 2 minus the actual temperature. So if I know my temperature ratios, then I can get my efficiency, and from that I could propagate it into my overall efficiency in terms of pressures, because that's what I have. I have RD, and I need to somehow incorporate RD into this equation. That's stagnation pressure losses. So I already know from isentropic relations, TOS over TA is equal to PO2 over TA, gamma minus 1 over gamma, and T stagnation 2 over TA is equal to 1 plus gamma minus 1 over 2, and 2 squared, and PO2 over PA is equal to PO2 over POA multiplied by POA over PA. Since I already know that PO2 is equal to stagnation T A. So from that, my overall efficiency in terms of my pressure loss is equal to 1 plus gamma minus 1 over 2 Mach number squared RD to the power of gamma minus 1 over gamma minus 1 over gamma minus 1 over 2 and squared. This is equation 6.6. That's just an efficiency loss that is associated with the diffuser, given the fact that you have shocks at the event. Combustion chamber. So from 2 to 4. We said total pressure losses due to flame holder drag. And obviously injectors as well. So I have a situation where it's a straight duct, like you just did in your sand number control volume. So PO2, M2, PO2, M4, PO4, PO4. So I have some pressure stagnation loss, RB. RB stands for burner, is equal to P stagnation 4 over P stagnation 2, which is less than 1. So RB burner. Generally, combustors are somewhere between 0.8 to RB of 1. That's actually what we do quite a bit of research in our lab, is trying to improve this overall pressure loss through some of the characteristics of this combustor right here. This is huge because it reflects 35% decrease in overall thrust if you're not burning efficiently and you're having a significant drag here. this drag alone of the flame holders that you have will result in a 35% reduction in your overall cost, although you're burning the same fuel. So, from that, we can translate that information into overall efficiency. See exactly how we just did it. But the difference is I have a burning rate. I can say, well, if I have complete combustion, what do you have complete combustion? Bless you. Then I have my fuel to air ratio that I'm putting in multiplied by my heat of combustion, which is the heat input of the fuel that I'm putting in, is equal to my overall 1 plus F, the mass enthalpy at 4 minus enthalpy at 2. Again, this is problem 2, was it the 4th question or the 3rd question? I think it's 3rd question, right? Where you have to do the equal to heat of combustion. And most of you said, oh, I'm gonna take it as Cp delta T, right? And you didn't take into consideration the kinetic energy. Right. So this is assuming ideal combustion. Now, if it's not ideal, or if combustion is incomplete, here's what Jason's working on right now. Here's what's incomplete combustion. So F has to equal to less than F, meaning that if I have the amount of fuel air ratio I'm putting in my combustor, and I have my heat input, that assumes that I take all my fuel and burn it and generate heat. Now that's not exactly what happens, depending on the mixing, because this is a high-speed flow that is going through this. Specifically for rapids, this is actually a Mach 0.3, which is about 125, 130 meters per second, which will translate to about 100 miles per hour. So it's moving really, really fast inside, and you need to mix and burn at the same time that whole fuel and air. That doesn't happen. You don't get this situation. You always get this situation where you're not producing enough heat from the engine itself, from the combustor itself. And again, this is another area of active research to determine how much are you burning and how can you improve it through the fluid tanks that you have within the engine mixing and so forth. So our combustion efficiency becomes a burner is equal to this over this. 1 plus F H4 minus H2 over we already know the fuel air ratio is equal to my stagnation temperature ratio minus 1. This is an equation that we've written before. HLP delta Cp CO2 minus TO4 over T. So exactly the same equation we had before. The difference is we assumed that efficiency was 1 before. But if you look at right here, so this is the example problem that we've done last time. This is the fuel air ratio. It's exactly the same as this. The difference is now I have to deal with an efficiency term right there. That's when I'm not bless you. That's when I'm not burning the fuel air ratio. So same thing, stagnation temperature within the burner is equal to TO4 over TO2. And that's primarily the losses across the burner. Now what I have left through the engine is my CD nozzle. That's another one. Make sure I don't